Okay, let's investigate work in a little bit more practical fashion by talking about something that may have a little bit more of a handle on. So, we have all seen a lever before. That's what this representation is right here. You can see it's basically just a seesaw, and I've got some objects of different weight over here, or sorry, mass, I should say, but they do have weight. And so if I put one of these objects onto the seesaw, you can see that it causes work to occur. Work occurred when I put this object on because there's a force of the object being pulled down. You can see that force here, and you can see that the seesaw was actually, or the object was moved through a particular distance, and that distance is right here. So you can see at the rest line, if I were to draw just very simply something that represents where it started. Sorry, I'm trying to get my bearings here. I'm going to use red as our color for right now. So it starts here. That's where it starts. Let's go ahead and throw it up on there. And let's see where it ends. It ended somewhere down. Ooh, I'm still trying to figure out where the heck I'm at. Right over here. So it went through this distance right here. You can see it did it in a curve. It traveled over this distance with some amount of force. Okay, well that's interesting to note. Is there a way to equalize or to do an equal amount of work on the other side using these other objects that we see to try to keep this seesaw balanced? So if I'm going to do positive work on this side because the object's moving downwards in the direction of force, can I put some other force over here that counteracts the work that's being done over here and does negative work to make it so that the object is balanced? Well, let me see. Let's put a 5 kilogram mass on this side, and we can clearly see that this force is not sufficient to do any appreciable work on this system. Let's put another one on there. And we can see now some negative work is being done because I've changed the amount of distance that this object has now moved. But not enough work has been done in order to make this fully evened out. All right, so let's contrive for ourselves a situation. So you can see now that if I just let the fire extinguishers do their thing, they are actually doing negative work because we got a force pulling down. We got a distance that this object is also moving. So let's take a little bit more rational approach to kind of looking at the numbers of this particular situation. And to do that, let me go ahead and restart my visual here. Okay, so what I want to do is I want to get to a situation in which I have one fire extinguisher on the very lastmost piece, and we can see that fire extinguisher will move. Let me place it here because it's actually easier to grab onto. But if I come into my simulation up here, my visual, we know that our fire extinguishers are going to start right here. Let's see where it ends. Let's go ahead and throw that on there. We can see now that the fire extinguisher has moved to right here. Come on, pen, wake up. I get it to focus in this program right here. That our fire extinguisher has moved here, and it has gone through an arc right here. That is now its distance that it wants to move. And likewise, we're going to have our trash can on here somewhere. So here's our trash can. We're going to try it in some different locations to see if we can equalize this work. So currently this was way too much because we're not balanced. So we want to move this down through this set of different locations, and we're getting closer until the work on both sides actually equalizes. We're getting much closer, and now we can see that it looks to me like we are balanced. So if I were to take the fire extinguisher off completely, I would see now that for my not my fire extinguisher, but my trash can, this object, and I'm having that focus issue again, this object will have gone from here. Let's see where it goes back to, that rest line is, to right here. And you can see, look at this. Let me move my fire extinguisher out of the way so you can see a little bit better. You can see that when I'm on the outer extents of the lever, that the distance that I sweep out is much larger than the distance that I sweep out when I'm on the inner extents of the lever. If I went even further in, I would see that this change in distance is even much smaller than what I just saw. So what I want you to realize is that this distance versus this distance, these two are not the same when this lever is in balance. So let's go ahead and put our objects back in the same places that we just had them so that it is balanced. I'm going to go ahead and pop up a ruler. And what I want you to recognize about this ruler is that it's showing some distances out from the center, the fulcrum point, the pivot point of this particular lever. And though those distances aren't directly exactly this distance right here or this distance right here, they are a really good representation. They are related to these distances. At least they're proportional to these distances. This one right here, the object is 2 meters out from the side. This one over here, the object is 1 meter out from the fulcrum. You can see that this line right here, this arc, is about twice the size of that arc right there. And in fact, I'll tell you straight up, they are exactly, this arc is exactly twice the size of this arc right here. So there's a proportionality that we can use to kind of explain this a little bit further. So what I want to do then is I want to go ahead and erase, create a new layer for myself so that we can do a little bit of art. That did not work like I wanted it to. Okay, let's undo that, because that wasn't right. We'll just undo. How about that? Told you, I'm not super swift at this yet. Trying my best over here. Okay, so what I'm going to do is I'm going to subdivide my stage into two parts. We're going to have the part with the trash can on one side, and we're going to have the part with the fire extinguisher on the other side. And what I want to do is I want to compare the amount of work that's being done on one side versus the other. So in order to do that, we need to understand a couple of things. First off, any forces that are occurring on this lever are purely due to the acceleration due to gravity working on these two objects. So if I just put the fire extinguisher on this lever, I could expect that the force of gravity is going to be pulling it down. So let's figure out what that force actually is. It's the weight of the object. Well, to do that, I need a couple of things. I need the mass of the object, which I know that the mass of the object is 5 kilograms. I need the force of gravity. And in the past, I've told you that the force of gravity is 9.8. Not the force of gravity, the acceleration due to gravity is 9.8 meters per second squared. But for today, just for the example that we're working on, let's round that off to a nice even 10 to make the numbers a little bit more easy to grasp and to work with. So let's say that g is 10 meters per second squared. So this mass is accelerating downwards with some sort of force. And we know that F equals ma, and so then I have 5 kilograms times 10 is going to give me a total of 50 newtons of force acting on this object. Well, I also know that work is equal to force times distance. Now, I don't have the direct distance that this object has traveled out, but I do have the proportion to the object on the other side. So I'm just going to assume that this 2 right here is the same amount of distance that it's actually sweeping out. It's not, but we'll use it just to make this a simpler problem. So if that's the case, then I can then say that the force that has been exerted is 50. The distance that it's traveled is 2 meters. And so the total work that has been done, 50 times 2 is 100. There are exactly 100 joules of work on this side that are related to that fire extinguisher sitting on that lever. Let's compare that work to the other side. So again, we have the mass of the object, that is 10 kilograms. We're going to use g as our constant. We know that F equals ma. And so then F is going to be equal to, in this case, 10 times 10. And 10 times 10, as we know, is 100. So that's got a total of 100 newtons of force sitting on the other side. We're going to come on over and we're going to figure out its work. Its work is equal to its force times its distance traveled. If that's the case, then that is going to be 100 times 1. Because if you look, there it is, sitting on the 1 meter mark. So if that's the case, then my total work is 100 joules on this side as well. Now this shouldn't be too surprising because we can clearly see that the lever is balanced. And so the reason why the lever becomes balanced is because the total negative work done on one side is equal to the positive work that would be done on one side if these could be moving. Okay, now does that always apply? Is this always true about levers? Is how much work I do on one side always equal to the amount of work that's done on the other side? Well, in order to answer that question, we're just going to have to contrive some sort of situation in which maybe that's the case or maybe it isn't. So let me go ahead and undo all this stuff again, because apparently creating a new document is not working for me. Maybe it won't undo it. I don't know. You know what? This is taking too long. Let's do it this way. Let's just throw down a layer. Oh my god. What have I done? Pop back in. Oh my gosh. You know what? Okay. No. Fine. You do your thing, Photoshop. You do whatever it is you want. And then we'll just size this up appropriately. How about that? Why it wants to go. There we go. Alright. We're happy again. Fun times. Okay, so let's set up for ourselves a new situation. Let's say we're going to move now. Let's move the 10 kilogram object all the way to 0.5. And we can see that some work is done. It's swept out some small amount of distance. Let's go ahead and see where we need to balance these 5 kilogram fire extinguishers to make this actually balance. So I'm going to go ahead and throw it down. I'm going to find the place at which it balances. It's not quite here. It looks like it's right there. And let's do the same sort of analysis that we just did. So if I do that, I'm going to come back up over here. Grab my pen. I'm going to divide this. Let's use black this time. Make it a little bit more visible. I'm going to divide this in half. Okay. And we know that the force acting on that object is going to be equal to its mass times the acceleration that it's experiencing. In this case, that acceleration is g. So in this case, that is going to be 5 kilograms. Come on, computer. 5 kilograms times 10 meters per second squared. Because we agreed we were going to use 10 meters per second. So if that's the case, we are experiencing, again, 50 newtons of downward force of weight from that fire extinguisher. Work done is going to be equal to that 50 newton force times the distance traveled. So again, we're going to use this 1 meter as our stand-in for the distance. So 1 times 50 is equal to 50 total joules. So there's our answer for the total work done on this side. Let's compare that to the other side. Again, F equals mg is the weight of the object. For this object, that is going to be 10 kilograms times 10 meters per second squared. That's going to be equal to 100 total newtons of weight. The work done by that object, if the fire extinguisher was gone, would be equal to 100 newtons times, and if we look very closely, it's now sitting on 0.5, so this should be 0.5. Come on, pen. 0.5. So 100 times 0.5, that's going to give me 50 joules. So it looks to me as though in every situation in which we have balanced a lever out, we actually have created a situation in which there is an equal amount of work that is being done on both sides. So this is going to lead us into tomorrow's lesson talking about what's called mechanical advantage and how work plays into the idea of mechanical advantage. I'm going to give you a little bit of a lab to work on tomorrow, and then that will hopefully show you some of the ideas of mechanical advantage, and then you're going to be working on maybe a graphic organizer as to how the other simple machines, like the lever, like the pulley, like the wedge, all produce that sort of equal work on both sides, but by changing the force and the distance that objects travel, because that's really what we've done here. Basically what we've done is we said, okay, let me take a small force over here and apply it over a long distance, okay, 1 meter is longer than 0.5 meters versus a larger force applied over a much smaller distance. So there's a little bit of give and play here and how that works out. All right, I'll see you guys tomorrow.